In the last video, we introduced value at risk and did some examples on how we can compute VaR. In this video, we will study something slightly more advanced. The first one is several properties of VaR. Namely, we want to check what kind of axioms we introduced previously are satisfied by VaR. And then we come to an important conclusion, that is VaR is not coherent. Okay, so let's say what axioms are satisfied, what are not. So here we claim that VaR satisfies 3 out of the 4 axioms of coherent risk measures. It satisfies translation invariance, positive homogeneity, monotonicity. So what is missing? Sub-additivity, right, or convexity. So now let's check, okay, whether those are indeed correct. First, notice this. Okay, this is rather obvious, right? That's because let's say you have this. The meaning is, by the way, since so we still write it, okay? So this is the definition. Just assume this is a continuous random variable, okay? So I can take equality. It helps us simplify the proof. So now I want to study the probability distribution for x plus a. So I want this to be still equal to the same level, but less than something, right? So obviously this means right. So now we can add a on both hand sides. So this is capital X, right? And because equality is taken, so this whole term is the new quantile of x plus a, right? So it's the still the delta quantile, but of the new random variable x plus a. So we have this this equality in general, and using this, we easily derive that the translation invariance holds, because this is exactly the definition of translation invariance. Next, we need to study positive homogeneity, right? So we can do something similar. Now what we want is, so we are looking for something down here. Let's call it y, right? And then y would be the quantile of lambda x, okay? And because this lambda is positive, I can easily divide this lambda over to the other hand side, right? Now I'm looking for the quantile of x, okay? And obviously this is just given by this, using our notation. So y divided by lambda equals the quantile of x. So now my y would be lambda times the quantile of x. Y is the quantile of lambda x. So this is checked. So positive homogeneity also works, right? Lambda has to be positive, because when lambda is negative, I will need to flip the sign of this inequality. Then everything changes. If lambda is 0, I can't even divide by it, right? Monotonicity is also easy to prove, right? That's because let's say we have this. So this is by standard definition. This is how we define quantile. Now I have, so given this and x less than y, okay, I want to look for the quantile of y, and I want to show it is greater than it. greater than the quantile of X. There are different ways to prove the first, but no matter which one you choose, you will need to write down the definition, right? So this less than, let's use small y, anything, okay? If y is less than it, then not equal. So what I need to do is to ask you, among these two probabilities, which one is bigger, right? If you are able to figure that out, then everything's straightforward. So I claim, right? That's because X is smaller. So for any small y given, is more likely that big X is more than Y, then big Y is more than Y. Okay, that's because this is bigger, right? With that in mind, if you plug in Y, if you plug the quantile of X for Y, then you will get right-hand side is delta greater than P of Y less than the quantile of X, right? And if you want equality, then this guy has to go up because cumulative distribution function is non-decreasing, right? So it's increasing. So in order for your level to go up, you have to increase the argument, right? So that's why the quantile of y should be greater than the quantile of x for the same level. So we just proved it satisfies these three axioms. And then we claim that it does not satisfy subadditivity. Right? And to show this, we just need to come up with a counterexample. Right? And here is it's a very famous example from the classical paper 1. So let's take a look at this counterexample. It has some financial background, but essentially everyone should be able to understand, even you don't know what an option is. Here is a special option called the digital option. But anyway, it doesn't matter. You can simply think the payoff is given by this. So we have this option A. The current price is small u, not small u. So this we can put small u. That's okay for this. So basically, the setup of this option is this is the future price, the stock price at the maturity time. So capital T is the maturity time. So if the stock price at the maturity time is bigger than some level, okay, so this is a threshold, it's a constant. So let's say let's set this upper bound to be $100. That means if the stock price at capital T is bigger than $100, you will receive $1,000. Okay, but if the price is below this you get nothing. So that's why it's kind of like a gamble, right? You gamble whether the stock price at some future time will be bigger than the threshold or bigger than the upper bound or not. Okay. Next, let's look at a different option B, which is similar to option A, except now you bet on the downside. So here you bet on the upside. So I use capital U to denote the threshold. Here I bet, or you may bet on the downside. If the stock price is less than some lower threshold, you will receive $1,000. But if the price is bigger or equal to this bond, you get nothing. Okay, and because in both cases, you don't lose anything, right? You either receive $1,000 or nothing, but you don't lose any money. Similarly, you either get $0 or $1,000 because this has value to you, right? So you need to pay. You need to pay for A and B. The price of A is small u. The price of B is small l. So that is the setup. So basically, you can think this as a lottery, right? So you pay U dollars to buy lottery A, and for lottery A, you can win $1,000 if the stock price at the expiration time is bigger than the threshold. Similar explanation also goes to lottery B, right? This is the price you pay. Once you have paid this price, you are entitled to this lottery. And this lottery might give you $1,000 if this happens, right? If it doesn't happen, you simply get $0, right? You throw away your lottery ticket. Okay, suppose this is obvious, right? So the upper point is bigger than the lower point, and for simplicity, we actually assume both probabilities are equal. They are 0.8%, so it's a small probability event. Let's select the level to be 99%. As mentioned, we usually look for big delta because that represents the bigger losses on the right-hand side. So now let's analyze, okay? So the first decision, like, we are on the sell side, okay? So let's say we sell one option A, denote the loss by LA. So let's write down what is LA. Okay, this means because we use LA to denote the loss. So negative loss is profit. So when do I earn profit U? Is when the stock price is less than or equal to the upper bound, right? Because then this lottery is worthless, right? It doesn't worth anything. So I simply pocket the price, right? Because I'm on the sell side. I sell this lottery to you, okay? So I receive U dollars from you, and if the stock price is less than the upper bound, your lottery is worth nothing. So I don't need to pay you anything, right? But I have already collected U dollars from you. So the profit for me is U, so the loss is negative U. And we know the probability is 99.2%. That's because the other side is 0.8%. Okay, but if the stock price is bigger than you, I will need to pay you $1,000. So my loss would be the payment, $1,000 minus what I collect from you, right? So there's 0.8%. Okay, similarly, I can do the same analysis when I sell one option B to you. Everything the same. Is I will get L dollars profit if the stock price is greater than or equal to the lower bound. The probability is 99%, 99.2%. And if unfortunately the stock price moves below the lower bound, I will need to pay you $1,000. So my loss would be the payout minus the original price of this option. Okay, so those are the separate businesses. Okay, now from here we can already calculate the VaR. For instance, delta is 99. Okay, what would be the number? You need to calculate to get the CDF, right? But first of all, we should know, right? This is bigger, right? So when you do the computation, it would be let me write it here, okay? So it will be 0 when x is less than negative u. Okay, it will be 99.2 when x is greater than negative u, but less than negative u plus 1000. And when it is greater than 1000, not 1000, there is 1. When x is greater than when x is greater than negative u plus 1000. Okay, so now I want 99%, so I want the smallest value to be bigger than 99, so it is negative u, right? Because at negative u, I'm actually 0.2% extra, right? I'm actually on the generous side for 99%. Similarly, for this, it's very easy to see that the 99% level would be negative L, right? The analysis is exactly the same, right? This is enough. This one is bigger than that. Now, okay, I sell both A and B at the same time. One ticket of A, one ticket of B. So now let's call this L A plus B. Okay, stock price can be more than you, or can be less than you, or can be in between. So now we actually need to discuss 3 scenarios. So first, let's still say when S is greater than U. When S is greater than U, I will need to pay this amount to the buyer of option A, but I don't need to pay anything to buyer of B. So it will be negative U minus L plus 1000. I have one payment to A. This is to A, not B. Then I discuss when S is between L and U. Okay, because it's less than U, so I don't need to pay anything to option A. And because it's greater than L, I don't need to pay anything to option B. So I just keep my profits. So last is when S is less than L. I keep the profit from A, but now I need to pay 1000 to option B, right? So as you can see, they are the same. So I can actually collect them together. So now let's study the CDF. So again, it takes 2 values. So we need to figure out the smallest value is negative U minus L. Okay, and when X is greater than negative U minus L, but less than negative U minus L plus 1000, the corresponding probability is this part, right? This part is, here I have 0.8%, here I have 0.8%, which means in between I have 98, I have 98.4%. Okay, finally, it is when X is greater than or equal to negative L minus negative U plus 1000, this is 1. Okay, now I still want 99% for the aggregate business. Okay, I need something bigger than 99. So I have to go to the last piece, right? Because now I only have 98.4% for the middle piece. Previously, I have 99.2%, right? So it gets lowered because for each business, it's like when I draw this, here I have 0.8%, here I have 0.88%. Previously, only one tail is used, right? If I sell option A, I'm worried about the right tail, right? It only has 0.8%. If I sell option B, I'm worried about the left tail. It only has 0.8%. Now, if I sell both A and B at the same time, I'm concerned of both left and right tails, and the probability together would be 1.6%, right? Double the original one. So now what I have is, right, negative U is the quantile of LA, negative L is the quantile of LB. So this obviously is greater than the corresponding quantile of LA plus the quantile of LB. So obviously we have a counterexample to sub-additivity, right? Sub-additivity says this should be correct, but now we have exactly the opposite side, which is true. So we have a counterexample. So it's not good. In the last part of this video, we are going to discuss some estimation. Those are from the mathematical point of view, and they are rather naive. So it's not what the industry is using. But anyway, I think it's still a good idea to understand the basic mathematics from these methods. The first one is called historical data. So what we do is we use data to estimate quantiles, right? It's just a naive idea. Let's see how this can be implemented. So let X be a loss amount for a certain period. Say 1 year, 1 day, you fix the period, okay? And assume that you have enough observation, you have N observations, okay, what you have observed previously, okay? You have N observations, so we sort them in ascending order, so from the smallest to the biggest, okay? So now let's select a level, say 95%, 99%, whatever you want. According to quantile, here we apply the so-called empirical distribution. So each observation has the same weight, 1 over n, right? And if you want, let's say 95%, it would be exactly the 95th observation, right? Because that's how you get the probability, right? Because they share the same weight. So 95th means including itself, there are 95 observations less than or equal to this number. So 95, and assume you have 100 observations. That gives you exactly the 95%, the level you want, okay? But sometimes when we apply the, when we use delta times n, you might get a non-integer observation. So here we are lucky, we have 100 observation and we want 95th quantile. So the number is, we actually have an exact observation there. But sometimes we may be unlucky. Let's say we have 250 observations. We still want delta to be 95%. And when we do this, we get a decimal, right? It's between two observations. It's between 236 and 238. Okay, it's in between, and the decimal is exactly 0.5. So what we can do is we do a linear interpolation because it's 0. Let's say if I get, let's say 4, okay, it's between 236 and 237. Okay, so in that case, I'm going to apply 60% on 236 observation and 40% on 237th observation. That is because this number is actually closer to the left-hand side, so you apply more weight on the left observation, less weight on the right observation. Okay, so it's kind of like opposite because here is 0.4, so you apply 0.4 for the far side. More weight, 60% on the closer observations. This is how we calculate the quantile. Once you know quantile, you get the VaR. Okay. You can ignore the last part. So basically, the method we just introduced seems naive, right? This is how we can estimate VaR once you have a series of observations. The advantage is everybody can understand this method. The disadvantage is um, it's not robust. It's highly non-stable because, so let's say here's the case. You use a single point, right? Because this is a single point, which is the 95th observation after sorting in your data. So what if somebody made a mistake? So because those are recorded, right? So let's say someone did a mistake. So let's say this the whole data, okay, have been like collected over the last many years. So let's say last 10 years. Each year you collect 10 points. So maybe in 1 year, okay, the observer was rather careless. So he put additional 0. So let's say in that year, it could be 10, 11, 12, 13, and 11. Okay, let's say half a year, those are the observations. But in that half year, this observer made a huge mistake. So those are the true numbers. But he was so careless that he put additional 0 for each one, right? And then obviously those 5 numbers will be significantly bigger than the rest observations. So if you sort out, those will be the 5 largest, right? And by our standard, after sorting this would be this number, right? Because if you count from the big side, it will be the 5th largest, right? It will be the 5th largest, okay? But this could be just a mistake, right? This is a mistake, right? All the numbers are manually, mistakenly recorded, right? 10 times bigger. So the actual number should be 10 instead of 100. But if you record this, 100 becomes the quantile, right? But in fact, it could be much smaller than 100. So it's highly non-robust, but it's very easy to apply. So if your data is big enough, this is usually a not too bad method, right? Because let's say you have 1 million observation and you want 95%, okay? So because you have 1 million, so you have a lot of margin for mistakes, right? So you are picking something quite far away from the largest or from the smallest. So relatively speaking, uh, it's not that unstable if the number of observations is big enough. And then we have a very simple model. In the first method, we rely on data. There is no model. We do not make any assumption on the distribution of X. By the way, it's a huge advantage, right? That's what we usually call model free. But now let's assume your X follows a normal distribution, right? You only need 2 parameters, right? Mean and variance. So select level, okay? And all you need to do is to use any software to get you the quantile, okay? And then apply this to everything, right? If you don't know mu and sigma, you can use data, right? So you can use sample mean, sample variance, or sample standard deviation for sigma, right? Then you can easily apply this formula to calculate variant risk. Obviously, this is a very neat procedure, right? And it's also easy to understand. The question part from here, everything relies on this assumption. If X is not far from normal, then this works brilliantly, right? It's easy to implement. You only have 2 parameters to estimate, and both are easy to find out, right? Sample mean, sample standard deviation, while you need less than a second to get the result from any software like R, MATLAB, anything. You can get the result in 1 second. Then you have this formula to get you the value at risk, right? But in practice, we often don't know what kind of distribution this X follows, right? Here we propose normal. There are many different models you can pick, right? Normal distribution is not good because it's symmetrical and the tails are usually too light. That's why if you apply model, it's probably safer to try those heavy tailed distributions like the student distribution uh, and a lot more. But for all those are model based. Okay, meaning how good your estimation is pretty much relies on the choice of model. If you switch from one model to another, the result can be dramatically different. Even you have the same data to do the estimation on parameters. Right. So for anything with this, the question is how good your assumption is. If your assumption is good, then the approximation or then the computation will be very accurate. Okay, here I have something I call the modern method. They are not exactly modern nowadays because we come with a lot more generalizations. But basically, those are time series models. Sometimes we call econometrics. It's a field. So basically, what we do now is we can observe a huge amount of data, right? So we actually have a time series of data from the historical experience. We want to apply a suitable model for this time series. After we fit the model, we estimate. Wow. So there are many time series models, right? So you can begin with auto regressive model, what we call AR model. AR model is a linear regression. So it's regression. By the way, that's what most people do in machine learning regression. But of course, it doesn't have to be linear regression, right? It can be generalized linear regression, GOM, or even more complicated than that. But anyway, you try to regress, okay? Here we regress with itself. That's why it's called auto regression, right? Well, usually what we do is y equals ax plus b, right? We have an independent variable, we have a response variable, but here we regress with itself, the previous values, okay? So this is the current value. So what we think is the past can predict future to some degree. So that's why we regress with its past history, right? But we don't know how far away should we carry over this regression, right? So let's say our time unit is daily. So what I want to know is maybe yesterday's price affects today's, but probably last year's price may have little to do with today's price, right? So which means I don't want to go all the way to 250, but I want maybe go back 1 week, 2 weeks, right? So the important thing is to test the value of P, right? You can't just pick P by yourself. You need to do the root testing to see which one gives you the highest significance, right? But usually here we assume noises are more usually we call the white noise. It has mean zero, and the variance it actually follows this normal distribution. We can also do moving average. Okay, so once you get those errors, you can do another moving average. Okay, assume the the current level can be explained by the previous errors. Okay, this is the MA model, and then you can combine them, right? ARMA. Sometimes the time series itself is not good. Maybe we need to do difference. Uh, that's that's uh, um, that's what usually people do in finance. Let's say R is the stock price. Well, usually we don't directly do the regression for stock price, right? We do regression for return. Okay, you can either do simple return. Okay, this is just the I. Sometimes you even do log return, right? Those, because those usually helps us to smooth data, right? We have a smooth data that will help with the later on analysis. That's why we do the this I. I is the we do the difference, okay? And that's ARIMA. And then we have fancy Gauch model or Gauch model. Autoregressive is conditional heteroscedasticity. So if you are interested, you can probably Google. Right? So this Robert Engel and Clara Granger, they actually won the Nobel Prize for their work on establishing this time series models to deal with, to analyze financial and economic data. Nowadays, it's standard textbook material for any major in finance. Okay, you need to discuss. There are many generalizations. Okay, that's because we are trying to take care of the um, it's here. So here, it's the error, right? But sometimes we want to study this volatility. This is really the key, in finance, volatility, right? You must have heard about the volatility all the time from the Yahoo Finance, from Bloomberg. So volatility is something we really care about, and we want to take volatility into modeling. That is the key idea of Gauch model. I think that's good for this video. In the next one, we will study tail value at risk.